Hello there. Welcome to the fourth and last knowledge clip about the Gibbs free energy. The menu for this knowledge clip includes first, Gibbs free energy changes for chemical reactions. Second, we will discuss Gibbs free energy of formation to calculate the direction of any chemical reaction. Let's get started. So we start with the Gibbs free energy change for chemical reactions. Take an example chemical reaction. A reacts to B. Now A includes a given amount of reactants A. And those reactants A will have a certain value, a total free energy of the reactants on this scale here in kilojoule, which you see given by this blue line. As the reaction proceeds, there will be a change of the free energy from the reaction, which we call delta G, and then the products form B, and they again will have a new total free energy of the products. This value for the free energy change of reaction can be calculated with this formula. We simply take the value for the free energy of the products and subtract from it the free energy of the reactants. So you see nicely in this example here, the free energy of the reactants is higher than the free energy of the products. That means with a lower number for G, for the products, minus a higher number for the reactants, we will get delta G to be negative. And you remember, when delta G is negative, it means it's a spontaneous reaction that will take place that is capable of providing a certain amount of non-volume work to propel biochemical processes in the cell, for instance. So how do you calculate the value for the free energy of the products? You take this formula. In the formula, there is a summation sign. It says we are summing over all products I. And the sum includes the multiplication of the stoichiometric coefficient nu I for each product times the free energy value for that respective product. Simple as that. The same is used to describe the free energy of the reactants. We again sum over all reactants I and multiply the stoichiometric coefficient with the value of the free energy of each reactant I. Okay, let's look at an example. Our example is the hydrolysis reaction of ATP. So one ATP reacts with one water molecule to form one ADP and one inorganic phosphate. You remember the hydrolysis reaction of ATP is essential, for instance, for this kinesin motor protein to walk along the track here. And you may see these little yellow molecules that are coming from the surrounding, and then they land on those feet, and then they react. And the free energy change of that ATP hydrolysis is now what provides the non-volume work for this motor protein to carry out this movement. So let's calculate the free energy change of the reaction. We simply, as the formula here states, multiply for each product the stoichiometric coefficient, which in the product is 1 for both the inorganic phosphate and the ADP, with the value for the free energy of the ADP and the phosphate. And here comes the product side, 1 times the free energy of ADP plus 1 times the free energy of the inorganic phosphate. And now we subtract the same summation, but this time for the reactants. So 1 minus 1 times the free energy of ATP minus 1 times the free energy of water. So when we carry out this calculation, we will obtain a value for the free energy of reaction of minus 28 kilojoules per mole of ATP. So you see the free energy of the hydrolysis reaction is negative. That means it's a spontaneous reaction and it's capable of providing non-volume work to propel the motor protein. Excellent. Okay, but there's one thing you need to be aware of, and you already know it. from our last knowledge clip. The value of the free energy for each of those reactants or products, it depends on the pressure and the temperature. So when we calculate the free energy of reaction, we basically need to state, or we need to make sure that all values for G are at the same pressure and temperature. Otherwise, we subtract and add values that don't belong together, simply. So it needs to be at the same pressure and temperature. And to make sure that this always happens, chemists have introduced the so-called standard state. The standard state is indicated by this degree symbol up here. And the degree symbol is usually representing that this free energy state is at 1 atmosphere pressure and 298 Kelvin temperature, right? So whenever we have one of these values, we usually use the standard state for those. And depending on what kind of reaction you have, that standard state may also actually vary. So for instance, reactions that take place in solution, then the solubilized reactants in the solution must also, the standard state must also include at what concentration they are. Or if reactants have different states of aggregation, either liquid, solid, or gaseous, then the standard state must also include what state of aggregation that is, and not only the pressure and temperature. Okay, so that's one thing to be aware of. The second thing to be aware of is actually the free energy values. They are not known. We don't really know the absolute values for any of the chemicals, what this G value is. But the good news is, even though we don't know it, all we care about is usually the differences of the free energy for the reaction, so the delta G values. So what we can then do is we can set arbitrarily a value 0 for the free energy for the reactants and products. And that 0 point is chosen to be when the reactants and products are at their elemental state. That means, for instance, pure oxygen, pure nitrogen, pure hydrogen, or pure sodium for whatever component you have. For those elemental states, we say the free energy is 0. It is not really 0, but we just set it to be 0 as our reference state, right? This is quite useful, as you will see in the following slide. Okay, so as I just mentioned, we set the value for the free energy for elements to be 0, which you see in this graph here. So the free energy here is plotted in kilojoules per mole, and you see the values being negative here. But for the elements, such as pure carbon, pure hydrogen, pure nitrogen, or pure oxygen, the free energy value is set to 0, simply. Now, with this reference point of the elements, we can actually describe the difference of the free energy with respect to the elemental state. For instance, for the molecule H2O, water. Water is made of 1 H2 and 1/2 O2, meaning just 1 O. And you see the value of the free energy for water is different from the free energy of the elements by a certain amount. And that amount, that it is different from the pure elements, we call that the standard free energy of formation. The standard Gibbs free energy of formation, delta Fg standard. So any compound has a value for this delta Fg standard. Take, for example, leucine, an important amino acid used to make proteins. It has a lower value of delta Fg compared to water because it is made of more elements, simply. So going from the elemental state to the molecular compound, we will have a change of the free energy at standard conditions by this amount for 1 mole. Same for the important sugar glucose. It's an even more complicated molecule than leucine and therefore has an even lower free energy of formation. Sucrose is an even more complex molecule. It's just basically composed of 2 glucose units and it has a further lowered free energy of formation. So the standard free energy of formation, it allows us now to calculate the Gibbs free energy change of any reaction, and all the values for the standard free energy of formation can be found in long tables. They have been measured over the last decades by hard-working scientists in the laboratory, and they have been tabulated in big textbooks where you can find the free energy values of formation. And with those free energy values of formation, you can now calculate the free energy change of any chemical reactions based on the same formula that you saw on the previous slide by simply multiplying the free energy change of formation with the stoichiometric coefficient for each product molecule, and then you take the sum and you do subtract from that the free energy of formation for each reactant molecule times its corresponding stoichiometric coefficient, right? So if you want to know the free energy change of any chemical reaction, you just need to find out the values for the free energies of formation of the reactants and products and then execute this formula and you will get the value for the free energy change of the reaction. Let's look at an example. Okay, let's use this formula now for an example calculation of the free energy change of reaction. So what is our example reaction? We are going to form glucose and oxygen out of water and carbon dioxide. This is a rather odd reaction because what would typically be the direction of this reaction is that glucose and together with oxygen forms water and carbon dioxide by combustion, right? The oxygen oxidizes the glucose to form water and carbon dioxide. This is the so-called combustion reaction. It can be carried out in a laboratory in a so-called calorimeter, and then you can measure in the calorimeter the free energy of combustion. But that reaction that we look at here now is actually the reverse of the glucose combustion, so we call it minus the free energy change of combustion. Okay, so now to calculate that value for the free energy of combustion or the reverse free energy of combustion, what we need to do is to evaluate the formula. So first we need to multiply the stoichiometric coefficient of each product times its corresponding free energy of formation. So the first product is the glucose. So glucose is formed out of its elements carbon, oxygen and hydrogen, right? And it comes with a free energy change of formation at standard conditions, which we can find in a textbook. So that value is now our first parameter in our equation here, the free energy change of formation for glucose. And since the stoichiometric coefficient here is 1, we don't have to put a number here rather than only 1. Second product is oxygen. We are forming 6 oxygen as products. So we have to add 6 times the free energy of formation at standard conditions of oxygen. You already probably have realized it, that is 0, because O2 is the elemental state of oxygen. And as we've discussed on the previous slide, the free energy of formation for elements is 0, right? So principally what I can do is I can actually cancel this term out as it is 0. Excellent. Good. Those are all the products. Now let's take a look at the reactants. The reactants are water and carbon dioxide. So we need to find their respective free energies of formation at standard conditions. First, carbon dioxide. Carbon dioxide can be formed out of its elements carbon and O2s, and in the literature we will find a value for the combustion of carbon and oxygen to form CO2. In this example, we want to form 6 CO2 because we need 6 CO2 later to form the glucose and the oxygen. So we take this part of the formula and subtract it from the summation of the products. So the reactant carbon dioxide times its stoichiometric coefficient, which is 6 times carbon dioxide, times the free energy of formation of carbon dioxide. The second reactant is water. Water can also be formed out of its elements H2 and O2. So for that, of course, we also have a free energy of formation, which is equivalent to the combustion of hydrogen with oxygen. That value, now multiplied with its stoichiometric coefficient 6, gives us the part of the reactants that we need to also subtract here from the free energy of the products. Excellent. So now we look into the literature. We will find the value for the free energy of formation for glucose, which is minus 970.2 kilojoules per mole. We will find a free energy value for the combustion of carbon dioxide, which is minus 394.4 kilojoules per mole. And last, we will find a value for the Gibbs free energy of formation of water, which is minus 237.2 kilojoules per mole. Plugging in all the numbers gives us a value of plus 2,870 kilojoules per mole for the reverse of the glucose combustion. So you see, the reverse of the glucose combustion has a positive sign for the free energy. It means it's not a spontaneous process, right? Because you usually cannot just form glucose out of carbon dioxide in the air and water. That's not a stable state of glucose. Glucose has a higher free energy than the water and carbon dioxides together, and therefore it's only thermodynamically favorable to burn glucose into carbon dioxide and water rather than to form glucose out of carbon dioxide and water, right? And so the Gibbs free energy value is positive. Okay, so I want to highlight once more how amazing this concept is. So if you have any chemical reaction and you would like to know the Gibbs free energy change of reaction, all you need to know is the free energy changes of formation of the reactants or products and products. So then you calculate the free energy change of reaction and you will see what value it has, and you will also see whether it's positive or negative, which tells you whether it's spontaneous or not. Excellent. Okay, so with the previous calculation we found out the reverse energy of combustion of glucose. Now the free energy of combustion of glucose itself is actually the maximum non-volume work that we can get from burning glucose. So this, as you know, is essential in biological processes because it can be used to provide energy for certain biochemical reactions. So the maximum non-volume work from burning glucose is simply the negative of that number, which is minus 2,872 kilojoules per mole. So what I'd like to know now is how many ATP molecules can be produced from burning one molecule of glucose. I know I told you earlier that you can synthesize ATP based on a proton concentration gradient with these membrane proteins, but you can also, there are other machineries in the cell that synthesize ATP via the combustion of glucose. And now that we know the maximum non-volume work that the combustion of glucose can provide, we can look at how many ATPs we can get from that. So we know ATP is synthesized by combining adenosine diphosphate with an inorganic phosphate. And that is not a spontaneous reaction, so it has a positive value for the Gibbs free energy of reaction of plus 28 kilojoules per mole. So now to answer this question, we simply take the value for the maximum non-volume work of combusting glucose and divide it with the free energy change of reaction to synthesize one ATP molecule. And this division gives us about 102 ATP molecules that can be synthesized from burning one molecule of glucose. However, experimentally, it was determined that in cells, for instance, via the citric acid cycle, it's only possible to synthesize about 30 ATP molecules per glucose, significantly less than the theoretical value would be. So just as you see how machines in man-made machines have certain efficiencies that are not 100% but maybe only 30%, also biological machines that are used to synthesize ATPs, for instance, have a limited efficiency because they cannot extract all the non-volume work from the free energy change of a reaction. They can only extract a part of it. So nothing is perfect, also biological cells are not. So with this concept of the free energy change of a reaction equaling the maximum non-volume work that this reaction can provide, we can, for instance, now also take a look at how many ATP molecules are needed to synthesize a protein. So you probably know proteins are polypeptides. They are long chains of peptide molecules. And the peptide molecules are bound to each other. And in one protein, you typically have about 100 peptide bonds. So how is a protein made? You see this, you're going to see this in this video, which I start to play in a moment. There is a so-called ribosome, which is a machinery that uses the genetic code from the DNA, which has been translated to so-called messenger RNA, and that messenger RNA is seen here. It is being read out by the ribosome, and at the same time amino acids are brought via other proteins, which are shown here in yellow, to the ribosome, and then they are connected to each other in a sequence that is defined by the code that is defined in the messenger RNA. So I start this process now. You see how the amino acids are brought to the ribosome and how the mRNA is being read out. And at the other end of the ribosome, the protein starts protruding. It starts coming out. And with each readout of the messenger RNA, a peptide bond is formed. And each time an ATPs are consumed for this. And at the end, the protein is ready and diffuses away, and the next messenger RNA brings again the code for the synthesis of the following protein. It's a fascinating process, but it requires energy. And ATP is the source for that energy, simply. So forming one peptide bond connecting two amino acids together costs energy. It's not for free. You have to add about 17 kilojoules per mole of non-volume work to connect these two amino acids. And we know the hydrolysis of ATP to ADP and an inorganic phosphate, it provides about minus 28 kilojoule per mole of Gibbs free energy change of reaction of non-volume work. So now if we want to make one protein, simply 100 peptide bonds times 17 kilojoules per mole divided by the maximum non-volume work of the ATP hydrolysis gives us about 60 ATPs are needed to synthesize a single protein. It costs quite some energy. However, in cells, it's actually required to have typically 4 ATPs per peptide bond. So even though the peptide bond costs only 17 kilojoules per mole, while the ATP hydrolysis provides more than that, minus 28, we need 4 ATPs for each peptide bond. And again, that's due to the inefficiencies of this process, because there are other steps that cost additional energy that are needed to be carried out for the synthesis of this protein. So it requires about 240 ATPs typically to synthesize one protein in a ribosome. And it's quite energy intensive. For instance, a bacteria such as Escherichia coli, 95% of the free energy that this bacteria has available is needed to synthesize proteins. So protein synthesis is a quite expensive process, but as you saw in this knowledge clip, it is based on the non-volume work that is provided from the Gibbs free energy change of reaction of the hydrolysis, for instance, of ATP. Excellent. That brings me to my summary of the Gibbs free energy. So we have learned that the Gibbs free energy is a thermodynamic quantity that results from the combination of the first and second law of thermodynamics. It is expressed completely in parameters based in the system, right? We don't need to consider the surroundings, only the system provides the values to calculate the Gibbs free energy change. Moreover, the Gibbs free energy change provides a measure for the maximum non-volume work that a thermodynamic process can provide, such as a chemical reaction. And also it gives us an idea of the direction whether a process is spontaneous or not. So in the next knowledge clips, for the next lecture basically, we are going to find out the equilibrium constants for all possible biochemical reactions. Looking forward to that. Thank you for listening. See you next time.